Hi, this is Mrs. Nielsen with Chemistry Essentials. This is your notes on acid-base chemistry, and I have a pretty old school setup here. It's not very technology savvy, but I'm hoping this works and that you guys are able to get the notes from me since I won't be in class for the next couple of days. So here we go. The other day we finished up just the first half of the first page of our acid-base chemistry notes, and we did the basics. Strong acids, listed some strong bases. I gave you some examples of how an acid dissociates and how a base dissociates in water. Gave you an example of water acting as both a base and an acid, showing that it has amphoteric properties. And that's about it. So we're on to definitions of acids and bases. So the Arrhenius definition of an acid is something that produces hydrogen ions in aqueous solutions. And according to Arrhenius, a base produces hydroxide ions in aqueous solution. So we showed you that there's hydronium produced here as a result of this hydrochloric acid in water. Now, hydronium and hydrogen ions are used interchangeably in acid-base chemistry. So just remember that whenever you see a hydronium, that is exactly the same thing as a hydrogen ion, because hydrogen ions and water will make hydronium. And so since all acid-base chemistry takes place in the presence of water, you can use these two interchangeably. Also, just know that a hydrogen ion might also just be called a proton, because a hydrogen ion has lost an electron, and therefore it really is just a proton, because the most abundant form of hydrogen, the most abundant isotope of hydrogen, is protium, which has 1 proton and 0 neutrons. So therefore, these three things are kind of used interchangeably, so just feel comfortable with that and try not to get confused. Okay? The Bronsted-Lowry definition of an acid and a base says that acids are hydrogen or proton donors, and that a base is a hydrogen or proton acceptor. Now, I will tell you that there's another definition called the Lewis acid and Lewis bases, but that's actually beyond the scope of the AP chemistry exam. So you'll learn about it when you get to college, or if you're curious about it, you can always ask me in class. But this is what you need to know for the AP test. So acids will either donate hydrogen ions, or they will produce hydrogen or hydronium in aqueous solution. Bases will accept hydrogen ions, or they will produce hydroxide ions in aqueous solutions. And notice that I showed you how both a strong base and a weak base can produce those hydroxide ions back up here the other day when we talked about that in class. And then here we have pH of acids and bases. Remember that P simply means take the negative log of, right? So pH just means take the negative log of the hydrogen ion concentration. Or I could even say that's the negative log of the hydronium ion concentration. It really means the same thing, right? And then if I were to rearrange this equation, remember that you can also solve for the hydrogen ion concentration or hydronium ion concentration. And I'll write it over here because I'm running out of space. But we could also say that hydrogen ion concentration would equal to hydronium ion concentration, and that would be solved by taking 10 to the negative pH value. Okay. Anyway, the pH of an acid will lie between 0 and 7, 7 obviously being neutral, and a base will be 7 to 14. The strongest acid would be closer to 0, and the strongest base would be closer to 14. So on the opposite ends of the pH scale are where you have your strongest acid and strongest base. Now, it is possible to be off the pH scale, so know that that's a possibility, but don't worry about learning that for the purposes of this course. Also, I want to let you guys know that it is possible to have a strong acid with a low pH or a highly concentrated weak acid that has a very low pH. So pH is really measuring the concentration of hydrogen ions, which could be because it could be a low pH because it's a strong acid, or it could be a low pH because it's a concentrated acid. So you're going to explore that a little bit more in the simulation that you'll do in the computer lab on Friday. So it's not only the strength of an acid, but also the concentration that determines the pH value. All right, now let's talk a little bit more about the acid ionization constant, the Ka. And this is same exact stuff you learned in the equilibrium unit that we did in the past few weeks. So example number 1, I have hydrofluoric acid here. Now hydrofluoric acid, if it dissociates in water, okay, remember water's in the liquid phase here. Now hydrofluoric is a weak acid, and that means that we're going to have a two-way arrow here, and we're going to form fluoride ions and hydronium ions. Okay. Now if I were to write the Ka for this weak acid, it's going to be, I looked it up. You would have no way of knowing the Ka off the top of your head, but it's 3.5 times 10 to the negative fourth, okay, which is a really small number. It's less than 1. And so if I were to write the Ka expression for the dissociation of this acid, it's fluoride times the concentration of hydronium ion, product concentrations over reactant concentrations, just like that. Okay. Now this Ka value is very small. Okay, it's less than 1, and that tells you that it's weak. Okay. Now if I instead take an example of a strong acid, like hydrochloric acid once again, okay, again hydrochloric acid aqueous and liquid water, now I'm going to have a one-way arrow because strong acids, these 7 strong acids that we have up here, will dissociate completely. So they have a one-way arrow, and I'm going to get my chloride ion and hydronium ion, everything aqueous. And the Ka of hydrochloric acid is huge. It's like 1 times 10 to the 3, okay? It's really, really big. And so, you know, if this were a reversible reaction, I could write the Ka expression as being H3O plus times chloride ion over HCl, okay? But really, it's shifted so far to the right. I mean, if this were at equilibrium, then I could write this Ka expression. Sometimes we don't even have Kas for strong acids because they're so darn large. So your book doesn't even have Ka values for strong acids because they're so big and they're not really at equilibrium. Okay, but if they were, this would be the expression. You can see because it's so big, everything or most everything is in the product form, hardly any reactants. Okay, so when you have a Ka value that's less than 1, that would indicate a very weak acid, and a Ka that's greater than 1 would indicate a stronger acid. So Ka value is just telling you how easily that hydrogen falls off for the acid, how easily that hydrogen is donated. Okay, the larger the Ka value, the stronger the acid, and therefore the easier it is for that hydrogen to be donated and come off the rest of the molecule. All right, let's turn the page and take a look at the next page, which is all about titration, which you guys have been doing titration for the last couple of days, so you should be pretty familiar with this. You know, titration, also known as acid-base titration, is a lab procedure where you have a titrant with known concentration and an analyte with unknown concentration, and you combine them until you see an indicator change color, and that end point is when the indicator indicator changes color should be pretty close to the equivalence point in which moles of acid equals moles of base. And you can look here and read this yourself, the bullet points about general things about a titration. The first part is about choosing an appropriate indicator, okay, based on the strength of your acid and base. We've talked about this a little bit in class. Indicators themselves are weak acids, so they're reversible reactions, and that's why they can change colors in different solutions. And you guys got to expose yourself to this a little bit with the Le Chatelier's principle activity. You worked with some indicators and saw that they changed colors if you added more acid or base. And that was specifically at Lab Station A. You were doing that if you remember that. Indicators, therefore, will have a small Ka value to establish equilibrium. The indicator or weak acid is one color, and the conjugate base of that indicator is another color. And then each indicator has a specific pH range so that it changes color. You want an indicator that has a pH range that includes the pH at the equivalence point, if possible. If not, you want to choose one that has an endpoint that's really, really close to the equivalence point. And so you can find the different indicator ranges on page 783 of your textbook if you're interested. I think I've showed that to you in class a couple of times anyway, so it's something that should look familiar to you. There's some definitions here as well. The endpoint, the equivalence point, a buffer region is the range in which the pH of the solution stays pretty constant. That's that plateau phase of your titration curve. And then a graph showing how the pH of the analyte solution changes in response to the titrant added is called a titration curve. And you guys are all going to be making titration curves of your data in lab for this particular lab. So here's an example of a pretty good problem particle view. It says the analyte in the flask is an acid that will be titrated with a strong base. So my titrant here is, the titrant always has to be a strong acid or base, okay? It's always going to be strong acid or base. In this case, we say that the titrant is a base, okay? And then here, what's in the flask is called the analyte, okay? And in this case, the analyte is an acid, okay? And it says which mark on the burette indicates the amount of base required to reach the equivalence point. So if you count here, I have 1, 2, 3, 4, 5, 6, 7 different hydrogen ions in here. So there's 7 hydrogen ions floating around in that flask. Hopefully you can see that on your copy. It's a little faint here, but hopefully you can see it, okay? Now remember, the end point, or the equivalence point of the titration, is when your concentration of hydronium ion or hydrogen ion is going to equal your hydroxide ion concentration. In other words, moles of acid is equal to moles of base. Okay, so what we want to do here is count. 1, 2, 3, 4, 5, 6, 7. I'm going to need to add 7 moles of hydroxide, or 7 hydroxide ions, in order to neutralize each one of these hydrogen ions here. Okay, so therefore, which point on the burette indicates how much base is going to be required. I hope you guys can pretty easily see that the answer there is D. Okay, and remember, when you're measuring pH in a titration, you're always measuring the pH of what's in the flask, right? So there's your pH meter sticking out there. Okay. All right, next question says, write the Bronsted-Lowry equation for a phenol red indicator. Use the equilibrium to predict which way the equilibrium will shift when a strong base is added. And what observations would you see? So again, this is something you were playing with in the Le Chatelier's principle lab. So I'm just going to say here, since it's phenol red, I'm going to say that the protonated form, protonated meaning with the hydrogen attached, PR meaning phenol red, is going to look like this. And all acid-base chemistry takes place in the presence of water. Okay, and so here's my liquid water, and it's going to be a two-way arrow because this is a weak acid. Remember, the indicator itself is always a weak acid. And so when that hydrogen comes off of the phenol red, then I'm going to have some phenol red that's deprotonated. And again, that'll be aqueous. And then I'll have that hydronium ion that was formed. So basically what I'm showing you here is that the hydrogen from the phenol red came off and joined with the water molecule. So this is my acid, a weak acid, which you can tell from the two-way arrow, and this is my base because the water is accepting the hydrogen ion. And then every acid has a conjugate base, right? And every base has the conjugate acid. Okay. So it says here that my phenol red is actually red. Well, I don't know if it says this here actually. Yeah, phenol red is actually red when it's acidic. And, oh, I'm sorry, I take that back. I apologize. Phenol red is actually yellow in an acid. And it's red in a base. Pardon me. Okay? So, meaning when it's in the protonated form, it's yellow, and when it's deprotonated, it's red here. So it says, use the equilibrium to predict which way the equilibrium will shift when a strong base is added. So now if I add more base, what's going to happen here, and this is Le Chatelier's principle, if I add more base, what I'm going to see happen is this, if I add OH here, okay, hydroxide ions are actually going to, from the base added, right, are actually going to pull away this hydronium, and it'll end up forming water molecules, right? So I'll have the OH from the base, which I don't know if you guys can see that, there we go, OH from the base plus hydronium ions are actually going to form two water molecules. Okay, so that hydroxide is basically removing hydronium from the solution and forming water. Okay, because water is very much more stable than these ions are. And so what's that going to do? If I remove product, if you take product away, according to Le Chatelier's principle, it's going to try to make more of it, right? It's always going to try to undo whatever you do to it. So that's going to cause a shift to the right. Okay, which is exactly why it will be phenol red is red in a basic environment. Okay, so hopefully that makes sense. All right, let's go on. Part 3, titration curves. And you guys are going to be making titration curves of your data from the lab. So let me tell you a couple quick things about the titration curves. Firstly, the analyte type basically it's saying, is your analyte an acid or a base? Okay, this is going to be indicated by the initial pH. Because there's no titrant added yet. Okay, so wherever you have the initial pH here, right, that's the initial pH. Before I've added any titrant, that's going to tell you whether your analyte is an acid or a base, right? This one, you can see that it's an acid because it's less than 7, and it's got a pH above 2, so it's actually a weak acid that I'm starting with in my flask. I can tell very easily by looking at this titration curve, okay? Next, the titrant type. Again, remember the titrant must be strong. Talked about that a little bit in class today. I think it creates a nicer titration curve for you. When you add strong to weak, then you see a more observable change in pH. Okay. Now the titrant type is going to be indicated by the final pH reading. Okay, because the solution has excess titrant. In other words, by the time you've passed the equivalence point and you're up here, you've added so much titrant. You're way past the equivalence point. You've got way more moles of your titrant than you did of your analyte, and therefore the pH at the end is going to tell you what was in the burette. Okay, what was the titrant? All right, the equivalence point is, remember, and you guys should know this, the midpoint of the vertical section. Of the graph, and you can see that here. Okay, now you may not have a totally vertical section, more like this one is kind of sloped, and that's okay. Just kind of approximate the midpoint as closely as you can, and compare that with your data table from the lab and see how closely your endpoint matches the equivalence point on your graph. Hopefully they're pretty darn close. Okay. And then lastly, the buffer range. And next week is really devoted to us talking about buffers. But a buffer is something that will resist changes in pH. I like to think of buffers as like a sponge, okay, where it absorbs excess acid or base. We'll talk a lot more about it next week. But it resists changes in pH. And so the buffer range is what you see in this range right here on the graph. Okay, it's already labeled for you, and the buffer range occurs after a small amount of titrant has been added. A buffer will form. And so this is why we see the pH remains somewhat constant, even when a strong base is added. Strong acid or base, but in this case, it's a base. Okay, so that's what we call a buffer range. And like I said, we'll talk more about buffers next week. Okay, so here's an example. It says the figure below represents a titration of ammonia with hydrochloric acid. And write the balanced chemical equation for this titration reaction. Label the acid and conjugate base pairs. Okay, so ammonia, we have NH3, which is going to be aqueous because it all takes place in water, and hydrochloric acid, aqueous, and we're going to have ammonium formed and chloride ion. In other words, what's happening here is, again, my acid is going to be the hydrogen donor, the base is going to be the hydrogen acceptor. And what the acid turns into after it donates the hydrogen is called the conjugate base, and the base, after it accepts the hydrogen, is called the conjugate acid. Okay? And then it says match points A, B, C, and D on the curve with the appropriate description below. And I'm going to let you guys go ahead and attempt to do that on your own. If you want to pause the video, you can. But here, what we end up seeing as the answer is the C, A, D, and B. In other words, at the start, you can see that we start at a higher pH above 7, so that's how I know that ammonia has not yet been acidified yet. And then the buffering region comes after you start adding some titrant, and then the equivalence point occurs. You have equal number of moles of acid and base, and then lastly, you have more acid in the solution, and that's why the pH drops even lower. Okay? All right, last page here. All right, so now we're going to talk a little bit about polyprotic substances, and you guys got to work with one polyprotic acid in the lab, okay? Poly, hopefully you guys are familiar with the term poly. Poly means many. Okay. So polyprotic means many protons. Remember, protons and hydrogens are synonymous terms. So this means this is something with multiple hydrogens, right? An acid with multiple hydrogens. So polyprotic substances can also be titrated with a strong acid or base and can produce titration curves that can be analyzed in the same manner. The only difference is that since polyprotic substances can lose or gain more than one hydrogen ion, the curve will have 2 or more equivalence points. So this would be the titration of sulfurous acid with sodium hydroxide. You can see that it has 2 equivalence points because of those 2 hydrogens that are coming off. So here's an example here of a polyprotic titration. Okay, you can see that there's 2 equivalence points, one that occurs about right here and one that occurs about right here, right, the midpoint of the vertical section of the graph. And sometimes one vertical section is more pronounced than the other. It's just the way it works, right? So it says the pH of the analyte is initially right about here, right, which is 1.5. And it is weak or strong. Well, anything less than 2 is considered strong acid, right? All right, the titrant is the titrant an acid or a base? Well, hopefully you see the pH is going up, therefore the titrant's a base. What is the pH at the equivalence point? Well, this equivalence point seems to be occurring right here about 4, pH of 4, and this equivalence point is occurring at a pH of about 9. And then it says, what is an appropriate indicator to use for this titration at each equivalence point? So you'd first want an indicator that would change color around pH of 4, which if you looked at page, what was that, page 783 in your text, you'd see that perhaps brome phenol blue could be a good indicator